For viral diagnostics, we'll focus on the fact that these coronaviruses contain an RNA genome. It's about 29,000 base pairs, so it's a large genome for a virus. But it's just a sequence of ribonucleotides. And you know that the CRISPR-Cas9 can recognize a long sequence of double-stranded DNA, and it can cut it. Well, the next thing to recognize is that life is complicated. So I think we have a poster right over my shoulder here. This is one of our favorite posters because I've given you sort of a really brief, simplified description of CRISPR and how it works. But the fact of the matter is CRISPR is exceedingly complicated. So you may be disheartened to know that there's not just one CRISPR system, not just one CRISPR-Cas9. There are, dare I say, literally hundreds of different Cas9-like proteins that have evolved in different bacteria over all these eons of evolution. So, of course, researchers were not satisfied just to find one, which we now stereotypically refer to as Cas9, but they then started finding all these others. But they're called either Cas12 or there's another one called Cas13A. So they're very much like Cas9, and they recognize double-stranded DNA and they make a cut. But then something different happens after they make that first cut. So I want to try to explain the science here of how these Cas12 or Cas13A enzymes can be used to detect the presence of this coronavirus sequence. And there's a great sort of, I can't really call it history of science because it was only done a year or so ago, but it's a story of the process of science. So what I'm going to try to explain here in a few minutes is some work that was done at UC Berkeley. There's a young woman there named Janice Chen. She formerly worked with the Jennifer Doudna group at UC Berkeley. And she and her colleagues there developed one version of this technology that I'm going to tell you about. At the same time, there was another group on the East Coast at MIT with Feng Zhang's group. And they developed essentially a parallel system. But I'm going to focus primarily on the Berkeley group. And what they found when they were characterizing, I don't know if it was Cas12 or 13A that Janice was working with, but they were able to show, sure enough, that the enzyme was inactive until it detected a particular sequence. Let's say it's a 16 to 20 nucleotide long sequence from the coronavirus genome. And when it found that sequence, sure enough, it would cut. But the big difference was that once that Cas12 was activated by recognizing this specific sequence, it then became a non-specific nuclease. It started cutting any sequence of DNA that it encountered. Unlike Cas9, which is a very well-behaved enzyme, only becomes active when it binds to its target sequence. It cuts once, it releases, and then it looks again for that same sequence. Cas12, as well as Cas13A, once triggered, they become a non-discriminant nuclease. And there's an interesting analogy here. Firecrackers used to be sold not as individual firecrackers, but the fuses were all kind of braided together. So you'd have a long string of firecrackers. And my brother and I would save up our money so we could buy some of these packs of firecrackers. But being very poor, we then treated these very carefully, and we would untangle one firecracker at a time. And you'd light the fuse, you'd throw it away, and it would pop. And that's like Cas9. Okay, it binds once, it pops, cuts the DNA. But other kids, the town kids who had more money, they would buy these packs of firecrackers, and instead of shooting them off one at a time, they would light the fuse of this whole pack, and then they would throw the pack aside or in the chicken coop, and this thing would just start exploding. One would explode, that would set off the next one, so you'd have this like a chain reaction. So it was sort of like a non-specific, indiscriminate Cas12 that once triggered, once the first fuse was lit, then the whole string of firecrackers go off. I don't know if kids today could relate to that analogy or not, but you might try it on them. So, story of science then. Suppose you're Janice Chen and you're doing this, first person ever to characterize this strange Cas12 enzyme that they had found from some bacteria. And yes, they showed that it was specific, but once triggered by a specific interaction with the sequence, it became non-specific. Now, I suspect that if that had been me, the moment that I had recognized from whatever gel I was looking at that, this enzyme has now become uncontrollable, I suspect I would have been disappointed and would have said, this is a mess. I can't do anything with this enzyme. It's lost all of its specificity. But this is where clever people really need to be recognized. And it wasn't that Janice created a whole new piece of technology on the spot, but she was aware of work that presumably other people had done. And I'm making this up right now. I don't know exactly who developed the following piece of technology, but there were some people who had been working with nucleotides, double-stranded DNA like this. And you can easily modify a nucleotide so that it becomes a fluorescent nucleotide. So you can chemically modify this nucleotide so it has a fluorescent chemical group. And then the thing that amazes me is that you could also put on this same oligonucleotide, you can modify it in a different way down here with what's called a quencher. And this is another chemical structure that quenches fluorescence. So as long as this fluorescent group is within a certain minimal distance of this quencher, then all of the fluorescence that's being emitted here gets sort of sucked up by this quencher. So this molecule is not fluorescent. So this becomes a reporter molecule then in a viral diagnostic system that uses Cas12. We're pretending that's Cas12. So you throw a whole bunch of these fluorescent but not detectable reporter molecules into the reaction mix. And if the Cas12 can recognize a coronavirus sequence and become activated, then that indiscriminate, non-discriminate activity is going to start destroying this reporter molecule. So as soon as it starts digesting these two ends away, then this reporter, this fluorescent group here, moves away from close proximity to the quencher, and suddenly you begin detecting fluorescence. So you can have this tiny little reaction in the bottom of an Eppendorf tube where nothing fluorescent is going on. But if you trigger the Cas9 enzyme, the Cas12 endonuclease in that little bit of invisible clear liquid, suddenly fluorescence develops. And it's not quite like, a bright light comes out of the tube, but there are ways then that you can detect the development of this fluorescence where previously all of the fluorescence was quenched. Janice Chen has done a terrific TED Talk several months ago, and we'll put a link to Janice's TED Talk somewhere on this site, so you'll have a chance to hear Janice talk about this in more detail. Viral Diagnostics has been developed as a rapid test, as a point of care test. And when this was under development, maybe a year, 2 years ago, when we first started hearing about these groups working on this, the rationale for developing these tests were that, well, if we have an Ebola outbreak in, somewhere in Africa, in a village where there's no electricity, there's no refrigeration, there's no lab, we need to have a test that doesn't require refrigeration, doesn't require a thermal cycler, can be transported, and then used in about 15 minutes and then a flow strip, just like a pregnancy test, will either develop a band or not develop a band, depending upon whether or not this reporter has been activated. So the thought was that we want to develop these point-of-care rapid tests for use in underdeveloped countries so that we can detect these viral outbreaks. And who would have guessed at that time that the real need, the application in this country for that kind of a rapid test is to have those tests available to your students who in the morning, while they're getting ready for school, they conduct one of these tests, and while they're brushing their teeth, this little test is developing over here in the corner, and they just check it just before they're ready to walk out the door, and they can say, whoops, I appear to have contracted COVID-19, so I better get a confirmatory test, and I better stay home from school, or nope, I'm good to go. So if we had those kinds of rapid tests available at scale right now, then you wouldn't be teaching virtually. You'd probably have those kids in your classroom again. So the answer to all of this is science.